Back for another adventure with alcohols, phenols, and ethers, as well as thiols and disulfides towards the end. This is an alcohol. We know that because we learned that in the functional group section in the beginning. This is a phenol. We've talked about this in a chapter of benzene and its derivatives, as well as in the first chapter when we learned about all the different functional groups. And this is a special thing called an enol. So this is where we have an alkene with an alcohol. And a lot of times we're going to see that when we have a conversion of a doubly bonded oxygen and that double bond moves in the compound. So alcohols contain a hydroxyl group, this OH group. That's this functional group. It's polar because it has an oxygen atom with also has a hydrogen bond on it. So it's going to be soluble in polar solvents, and it can form hydrogen bonds with itself and other alcohols. And remember that hydrogen bonds are one of the strongest intermolecular attractions that we have. Now the R group of this one is nonpolar. Depending on the length of the chain, they're going to be soluble in water. So how many carbons can this one OH group pull into solution? About 5 to 6. So we'll see that happen. So hydrogen bonds, remember hydrogen bonds way back when? Well, we reviewed them, but we'll review them again real quick. Hydrogen bonds form between hydrogen directly bonded to nitrogen, hydrogen directly bonded to oxygen, or hydrogen directly bonded to fluorine. That's enough, or it's very fun. Yeah, I'm better in person. So if we have a really long molecule like this, and we want to put it and see what's happening in solution, we could actually draw and show the hydrogen bonds. So how we show hydrogen bonds, so this is an actual bond. There we're sharing electrons, right? Where we're sharing those two. But when we have an attraction, we use a dashed line. So that's going to be showing our attraction through maybe a hydrogen bond. Like we see here, this is our nonpolar section. That's where our London dispersion forces are taking place. But this is our polar head group here. And we're going to see that this hydrogen, I don't know why I like to draw these in red, but I do, is attracted to the oxygen. So this is another R group with an alcohol group. This is the actual OH bond. That's the covalent bond between the oxygen and the hydrogen. And the attraction from the hydrogen, the partial, if we have the partial positive and partial negative, so this is our partial negative and our partial positive, they don't have quite a whole ionic shift, ionic transfer of an electrons. We don't transfer an entire electron, but we have an unequal sharing enough that we're going to have a partial charge, right? So we have a dipole there. We can see the attraction to actually two different molecules because we have the hydrogen here, and sometimes this oxygen, depending on where it's at, can even be attracted to more. So here we have another attraction between the hydrogen of the alcohol group and another oxygen from another alcohol. Small alcohols up to 5 to 6 carbons are going to be soluble in water due to this attraction. They're polar. They can hydrogen bond with the water like we just showed with the alcohol. They can also do that with water. So 1, 2, 3, 4, that would be butanol, has a solubility of 7 grams per 100 milliliters. But let's look at this one. Here's our OH group. 1, 2, 3, 4. Oh, look at that. Another OH group. We didn't say you could only have one. This is very soluble. So having 4 carbons, we only get 7 grams per 100 milliliters, but this one is basically infinitely soluble. So every OH group can pull about 4 to 6 carbons into solution that we would not normally go with because of the R group being nonpolar. So this is very soluble. So alcohols have abnormally high boiling points due to their ability to hydrogen bond, and for their small molecular weights, they have very high boiling points. So let's take a look at this. This is our R group. So this is an alcohol. This is again our oxygen, and this is the attraction that we see that happens between the oxygen and the hydrogen. And here we would have the hydrogen attracted to another oxygen. So this hydrogen bonding is going to increase the boiling points of alcohols higher than we would even think they would be. So boiling point trends, we see this is what? 1, 2, 3 carbons. This is propane. And propane has a boiling point of negative 42 degrees Celsius. So what is it at room temperature? At room temperature, it is a gas. Okay, this is called an ether. I know we learned the functional group in the first chapter, but this is actually dimethyl ether. I don't really have room here. Dimethyl ether is the common name, but we would have methoxymethane as the IUPAC name. Negative 23 degrees Celsius. So we see that it's increased, but it's still a gas at room temperature. What happens here when we turn and move this oxygen over to be terminal and have that alcohol group? Positive 78.5. So at room temperature, it's a liquid. So 1, 2 carbons, 1, 2 carbons, same molecular formula between these last two, but look at the difference in the boiling point. So that hydrogen bonding makes a huge difference. Now, if you remember way back from chapter 1, or I don't say chapter 1, it's like a chapter 0 kind of thing, but we learned how to tell whether it was a primary alcohol, a secondary alcohol, or a tertiary alcohol, and I just want to review that real quick. So a primary alcohol, we can't look at the oxygen like we do for nitrogen and carbon. We have to look at the carbon that's bonded to the oxygen, because oxygen's only going to make those two bonds. So carbon that's bonded to the oxygen, how many R groups is it attached to? If it's 1, it's primary. If the carbon is bonded to 2 groups, it's a secondary. And if it's bonded to 3 groups, it's tertiary. How do we name alcohols? Remember, like we've been talking about, we take that same system that we learned for alkanes and we're going to adopt it to everything else in the future. So all we're going to do now is change the ending and what takes precedence. So we still have to find the longest chain. But now we have to have, just like we saw with alkenes, the longest chain that included the double bond, or the longest chain that included the triple bond. Now we need the longest chain that contains the OH group, so that alcohol group. The OH does not have to be on the end. That's important. It can be in the middle of the chain. We still have that. We follow the chain through. Now the OH is going to take precedence over all the other functional groups we've learned so far, and we're going to drop the E from the alkane name and change the ending to all. So we must then number where the OH group is. So we have to say, where is the OH group? Because it could be at carbon 1, it could be at carbon 6. If we have an alcohol that is a cyclic alcohol, the OH is going to be always at carbon number 1. It's defining carbon number 1. So you don't have to have a number unless you have more than one substituent. You'll have to number those. Now, sometimes we have more than one alcohol, as we just saw in the solubilities we were talking about. If more than one alcohol is present in the molecule, you just use the prefixes di, tri, and tetra, like we talked about before with we have more than one functional group. The IUPAC names for diols, triols, and so on are always going to retain that final E. So instead of dropping it like we do, so in methane, if we want to change it to methanol, I can show you like that. So methane, oh, whoops, I did that again. I'll get used to it eventually, someday. Methane would be meth, and we drop the E and becomes methanol. But when we have a diol or a triol, we do not drop the E. So here we have 1, two carbons with two alcohol function groups. So that was ethane, and we keep that E, we'll just add diol. So 1,2 ethane diol to get the correct name. Same for propane diol, and here we have 1, 2, 3. The oxygens are, the alcohols are at 1 and 2. They could very well be at 1 and 3, but they're at 1 and 2, so we need to put those numbers in there. And here we have 1, 2, 3. We have 3 alcohol groups. This is 1, 2, 3 propane triol is the IUPAC name, but glycerol is going to be an important thing we talk about. Glycerin also. This is glycerol. This is going to be a backbone for our fatty acids. So we have these really long chain fatty acids. We have a little thing going on here with an actual, there we go. So we'll end up having that glycerol be the backbone where these OHs are very, very important. So they'll be called glycerol. We'll talk about triglycerides and that sort of thing as we move forward. So what are some examples that we can look through? Let's try these ones together, and then I'll give you some to try on your own. So how would we number this chain? Let's try finding the longest chain. Here is the longest chain. It could go up instead of sideways, but that's fine. How many carbons is it? 1, 2, 3, 4, and we're going to start numbering from this side because it'll make our alcohol group have a number 2. If we came from the other side, it would have a number 3. So this is going to be changing the ending to all, and it's a number 2. And this is our methyl group. So butane is what we have here. But we're going to drop the E and change the ending to all. So butan all, and then we put our substituents in alphabetical order. But we only have one substituent in this case because this is going to change the ending. So we have butan all, and it's at number 2, and our methyl group is at number 3. 3-methyl-2-butanol. This is an example, the next one, of a cyclic alcohol. Remember, we said the alcohol is always number 1, 2, 3, 4, 5, 6. So we have a cyclohexane. We're going to take that E and drop it. We have a methyl here. And our alcohol is at number 1. We don't have to number it, okay? So we're just going to say that's going to change it to cyclohexane all. It's at number 1. We, again, don't need to number it, but we do have to number the 3, so we'll say 3-methyl cyclohexanol. So cyclohexane all. You don't need the number 1, so we can leave it off and put the methyl group there, and then we have a number 3. So 3-methyl cyclohexanol. Good. Let's practice some more. I would love it if you guys paused these, tried it, and then compared our answers. What happens if we have an alkene and an alcohol? Which one takes precedence? Well, if you remember from a few slides ago, we said that the alcohol was going to take precedence. We're going to start from the right for our longest chain, but we still need to include that double bond there. When we number, we're going to start numbering from the right. 1, 2, 3, 4, 5, 6, 7, 8. So now we have an ene, we have an all, and we have 8 carbons. We also have to remember, this is the part that I think most of us are going to probably forget if we forget anything, is let's look at these groups that are on the same side. So the same side means we have cis. So now we have cis. Let's put them in order. I think I actually have it in the PowerPoint, so I can just put it that way. But we have octane, I'm going to drop the E and make it octanol, but it's not an octane anymore, is it? And now it's an octene. That E is extremely important because it means we have a double bond here. Octene, we drop this E and add the ol for the alcohol. So how do we do that when we have two different things that are changing the ending? So it's kind of weird. We actually put the number between the N and the O. We're going to put the number 2 there. Octene 2-ol. And then we'll put the number 6 beforehand. So 6-octene 2-ol. Let's do another one. Common name for this is geranol. I probably said that just wrong. That's okay. I'm not very good at always saying everything the right way. Tomato, right? 8 carbons again. So what do we have here? We have a methyl group. We have a methyl group, but we also have 1 ene, 2 enes, and we have an alcohol. So we have oct for 6, but do you remember what we did when we have more than one double bond? We have that A, octa, di, ene. Now we're going to drop that E and we're going to add the number and put the 1-ol, octadiene-ol. I have to say where the double bonds are, so those are going to come out front. They're at number 2 and number 6. 2, 6 octadiene, 1-ol. And where are my methyl groups? 3 and 7. 3, 7. I have how many of them? I have 2 dimethyl. So octa, di, ene, 1-ol. The dienes are at 2 and 6. And then I have to say where my dimethyls are. They're going to be at 3 and 7. Alternatively, you can also do this where you put the 2 and 6 between the octa and the di, and then you're specifically saying that 2 and 6 is for the diene. So if you find this confusing, this is also okay. Even more practice. Now, if you haven't stopped and paused these yet, you need to do so. If you're wondering why you're not doing so great on tests or you're having a hard time keeping up, you want to make sure that you are stopping and you're pausing and you're practicing as we go along. So what is the longest chain here? 1, 2, 3, 4. So we have butane, but we're not going to have, did I count that wrong? 1, 2, 3, 4, 5. I did, I'm sorry. What is it now? It's not a butane, is it? What is it? 5 is pentane. I don't even know what made me look at that. My brain was like, no, stop. All right, so we have an alcohol at number 2 and a methyl group at number 4 that we need to add in there. So 4-methyl, 4-methyl, 2-pentane. We drop the E and add all, pentanol. Good. All right, here we have 1, 2. It's a 6-membered ring, so we have a cyclohexane. We're going to drop that E and change it to an ol. We don't need a number because the number 1 is not required because the OH is number 1. We do have 2 different facing groups. One is above the ring, one is below, so we have a trans we need to make sure we're putting in there. And we have a methyl group. This is a methyl group. feel free to draw this stuff out, circle it. I know it's harder on the computer, but that's how you're going to get it. So trans, we have the methyl group. What number is it at? It's at number 2. 2-methyl. And then what do we have? Cyclohexane, all, cyclohexanol, because we got rid of the E. So trans 2-methyl cyclohexanol rolls right off the tongue, right? Let's number our carbons. 1, 2, 3, 4, 5, 6, 7 is our longest chain, I think. But let's just double check. 1, 2, 3, 4, 5, 6, 7. This one's actually pretty simple compared to everything else we've been doing. We have 2 hept, and we drop the E, right? So we get rid of that E, and we change it to all, 2-heptanol. And the last one is, let's see, 1, 2, 1, 2, 3, 1, 2, 3. No matter how you go, it's 1, 2, 3. So we have 3 carbons, 1, 2, 3. We have 2 methyl groups, dimethyl, and we have an alcohol. So 2, 2 dimethyl. We have propanol, but it's at number 1. Now, some of you are probably saying, do we really need that one? Because technically it could be at carbon number 2, but it really can't because both of our methyl groups are there and it would give carbon 5 bonds. Yeah, let's just put it in there because we're supposed to number it if it has a possibility of being anywhere else. I hope that was good and sufficient practice. Here's some examples of alcohols that you might, I can erase the ink on the slide and let you see the ones that are in the PowerPoint, if it's better handwriting, I'm sure. All right. So some examples of alcohols. This is methanol. It's also known as wood alcohol. We use that in fuels and windshield cleaners. Now this is ethanol. I can't imagine anybody using that for anything. Can you guys think of anything that might be used for? I must not get out much. Grain alcohol. So fuel, a little bit, about 10% anywhere you go in Michigan. And alcoholic beverages are kind of a small, I guess, portion of what that ethanol might be used for. Might be larger during everybody staying home, huh? All right, we have 1, 2 carbons, and we have 2 OHs. So this is ethane diol. We had this one earlier. This is also known as ethylene glycol. This is what's in antifreeze and what they use to de-ice planes in some cases. 1, 2, 3. We have propane diol. We talked about this one a minute ago, but this is propylene glycol. It's actually a less toxic antifreeze. In case you don't know, you should never drink antifreeze because it will create little crystals in your brain and you die. That's not good. So it's also toxic to animals, so you have to be careful about leaving it around. But a less toxic version that will still lower the freezing point of water is going to be the 1,2 propane diol. And here again we have our 1,2,3 propane triol or glycerol. It's a moisturizer, it's a lubricant. It's also our backbone in fats. Sorry, I didn't mean to hit the microphone there. So very important uses. But, other forms of nature also use these alcohols in certain ways. So this is a fly. Hello, Mr. Fly. But for survival, and frogs do this too, and I would normally show you a video, so you can look it up if you want. I'll try to post it. A video on the North American wood frog, and that frog can freeze and then thaw. A lot of goldfish can do this as well, but we're not sure exactly the way it takes the process. So how they survive northern winters when it's very cold is many fish and insects produce a large amount of glycerol, and they dissolve that in their blood, and it lowers the freezing point of their blood. It's an antifreeze for their system. Well, that's cool, but is it important to anything else? Well, if we could figure out how it works, we might be able to undertake cryogenics. Do you ever see that episode of The Golden Girls where they're all coming back as heads? If not, I highly recommend it. Look it up. Okay, dehydration reactions. A dehydration reaction is where we're going to remove water. That little pause was me considering breaking this into 2 videos, but we're just going to keep going. So a dehydration reaction is where we're going to remove water. So we're going to remove water and form a double bond. Let's see how that happens. Well, that's why it's called dehydration. We're removing water. Convenient, huh? So we get a double bond, we get an alkene, and we get water. Sometimes, usually, these are done via acid catalyzed reactions. So dehydration from an ether, specifically, to form an ether, excuse me. Now, we want to dehydrate to form an ether as a product instead of an alkene. We have to be very careful how we do this. So it has to be done at a lower temperature, and this is going to be a limited form of an ether. You can only form symmetrical ethers when we do this. So we react 2 of these together with an acid catalyst around 130 to 140 degrees. So for these reactions, you are going to have to look at what temperature they're done at. When we do that, we will get a symmetrical ether. So this one would be diethyl ether and water as a byproduct. So what happens is this OH group from 1, and so these essentially go away to make water, and then this one comes in and bonds to the oxygen, forming the ether. We'll say essentially that's what happens. All right, so those are forming symmetrical ethers, or we can have the reaction that forms an alkene. If we go back here, we will talk about, oh, actually, we'll go forward. I have it listed when we go forward, I think. So dehydration, alcohols are dehydrated by heat and strong acid. What temperature is it being done at? If it's heated to about 180 degrees, you're going to get an alkene. If it's heated to only about 130, 140 degrees, something less than, 180, you're going to get an ether. Temperatures in between those two, you might get a mixture of both. So H2SO4 or H3PO4 are going to be required. We need that acid catalyst. Sometimes we can have more than one possible alkene product. Which one will be favored? Remember we had that Markovnikov's rule back for when we were forming our other ones. We have to look now and see what happens in this case. In this case, we're going to follow somebody named Saint-Sev. But let's take a look at what our possibilities are. So here, when I dehydrate, I'm going to dehydrate by taking another hydrogen. So I can either take this hydrogen or I can take one of these hydrogens here and the OH. That's how I'm going to get water. I need 2 hydrogens and an oxygen. So if I take this hydrogen, I'm going to get one product because the double bond will form here. If I take this product, if I take this hydrogen, I will get a different product because the double bond will form here. So when we do this, I want you to double check your notes just to make sure this says 180, H2SO4 and H3PO4, okay? All right, our products, if we take the first 2, here, if we take these ones, we'll get the double bond between these 2 carbons here and here. But we have that other option of taking the hydrogen to the right, the terminal one, and getting this double bond out at the end. So which one is going to be favored? Well, Saint-Sev, and I'll put it up here, Saint-Sev's rule says that the preferred product is going to be the more substituted alkene. The more substituted alkene. Does that make sense to you? Well, let's take a look at what we just had. So in that case, would it be this one or would it be this one? Which one has the alkene that has more substituents on it? Well, let's look at how many substituents. 1, 2, 3. So this carbon has 2, and this carbon has 1 for a total of 3. This double bond here, we have 1. So according to me, 3 is greater than 1. I hope you're with me on that one. So this top product will be our major product, and the bottom will be the minor product. So the more substituted alkane. Excuse me, alkene. I just said that. Let's look at another dehydration. So this one's being done. Why don't you practice and see if you can figure out what's going to happen here, but look at what is reacting. H2SO4 or H3OPO4, so we have a strong acid, and we have 140 degrees. And let's say we have unlimited amounts of this, so we have at least 2 if we need it. What do you think is going to happen? Well, I hope you chose the ether, the symmetrical ether. And what would this look like in line structure form? 1, 2, 3, 4. So 2, 3, 1, 2, 3, 4. Oops. Got a little crazy. I can't help it. Whoa. Go back. 4. We have our methyl group here. We have our oxygen here, our OH group, which is actually going to say form that, that, 1, 2, 3, 4, and we have another methyl group there. But that hydrogen is no longer there because it went to make water, so we do have a byproduct of water. Since there's only one product, it's not like the alkenes, there's no major and minor here. What happens if we try to dehydrate a ring? Well, where can my hydrogens come from in a ring? So I have to look at the adjacent carbons. So this is the carbon it's attached to. I need to look one up here and up and down here. Sorry, I should say down here. So which one? This is at 180 degrees, so we're going to get an alkene. I can form one product if I have the hydrogen leave from here. So if the hydrogen leaves from there, we will get a double bond between these carbons that looks like this. But if the hydrogen leaves from the bottom carbon, one of those two hydrogens, we'll get a double bond over here that looks something like this. So take a look, think about Zaitsev's rule. We want them more substituted. Since this one has a methyl group and this one does not have a methyl group involved in the alkene, the top one would be our major product and the bottom would be our minor product. All right, let's take a look at another one. Just because. If you have not yet done so, please pause it, and I want you to practice. Okay, so we have ethanol reacting at 180 degrees, so we're going to get a double bond. Where is it going to be? Ethanol becomes ethylene with a double bond between the two carbons. There's no other option here on this one. This is a nice easy one, plus water as a byproduct. Here we can take a hydrogen from here or here if we needed one to form a double bond. Or what's our other option? Because this is at 140 degrees, we're going to see 2 of these react to form an ether. So this is cyclohexanol on the left, and on the right we have diethyl ether. Oops, whoops, go back. This is cyclohex and all. And this is dicyc. Oh, whoops. I need to erase that. Dicyclohexan. Okay. Cyclohex ether. Common. Go common. It's fine. We're not naming them yet. We'll get to those. But that's fine for now. You wouldn't even have to name them. That's probably why I didn't put it in the slide. So we have here 1, 2, 3, or 1, 2, 3. Either way I go, there's 3 carbons. And OH, it's only at 50 degrees. But there's something about this. Let's take a look here. I have a hydrogen here, here, right? But where's it going to go? It doesn't actually matter, because if it goes here, here, or here, I'm going to get the same product, and that product is going to be 2-methylpropene. So no matter where I take the hydrogen from, I'm still only going to have one possible product. So that would be 2-methylpropene, our major product, if you will. Let's stop this video here for now. We'll talk about the rest of the reactions of alcohols when the next